So now we will see addition instruction. The opcode for addition instruction is add. Now addition, when we are performing addition, then we require two data which are to be added. So the two data can be in registers and can be in memory. So the format of this instruction is like this: register 1 slash memory, comma, register 2 slash memory. So now, so here there are two operand. This is one operand and this is second operand. So first operand can be in register or it can be in memory, and second operand can also be in register or memory. So various form of this add instruction can be: first, add the content of register 1 and register 2. Second, add the content of register 1 with memory. Third form can be add the content of memory and register 2. That's all. And fourth format, that is add memory content with the memory content. This is invalid. Means in memory some data is there and we want to directly add it with another data which is in memory. So directly, if two data are in memory, then we cannot directly add those data. One data must be in some register, right? So here, this instruction is invalid, so we will remove this. Now these registers can be 8-bit or it can be 16-bit. Or 16-bit, right? For example, 8-bit example, it can be AL, BL, DL, anything like this. And 16-bit means AX, BX, CX, like this. So, we will take the example for first instruction, add. Now here, first, this is destination and this is source. So what this add instruction will do, it will add the destination data with source data and result will be stored in destination. Right? So result will be finally stored in destination. For example, in first case, add the value of register with the value of another register. So add AL, comma, BL. So here both the registers are 8-bit register. So what this instruction will do, it will add the content of AL with BL and finally result will be stored in AL. Another example, add DL, comma, CL. So here this instruction, what this instruction will do, it will add the value of DL with CL and finally result will be stored in DL. So the result is always stored in destination. Another example of 16-bit register, add AX, comma DX. So here both the registers are 16-bit. So the value of AX will be added with value of DX, and finally the result will be stored in AX. So when we use add instruction, so if we are using registers at both source and destination, so size of the register must be same. If we cannot write this instruction, add AL, comma BX. So this will give error, because here what we are trying to do, we are trying to add the 8-bit register AL, the value of 8-bit register AL with the value of 16-bit register BX. So this is not possible. Now in case of second, examples of second form, add register 1, comma memory. So here one of our data is in register and second data will be in memory. And to access the data from memory, we can use, for memory we can use direct addressing mode. To access the data from memory, we can use register indirect addressing mode, or we can use index addressing mode. Any mode we can use in which we want to access the content of memory. So examples of second type is add AL, comma within bracket 1000H. So now in this instruction, first whether this instruction will perform the addition of 8-bit number or 16-bit number. This we can identify by seeing the destination. Destination register is AL, which is a 8-bit register. This means this is the 8-bit addition. So one of our data is in AL register and our second data is in memory at the offset 1000 of data segment. So suppose this is our memory. In this memory, this section is our data segment. Let the value of data segment register is 2000H, and in this data segment at the offset 1000H there is some data, right? There is some 8-bit value. There is some 8-bit value. So here the value of AL register will be added with 2000H colon 1000H, right? So we are having some data at physical address this. So that 8-bit value will be added with AL and finally result will be stored in AL. We will take another case. Add AX, comma, or here itself we will take another case. Add AL, comma, within bracket BX. So here our first data is in register AL, second data is in memory, and the offset address of the memory where our data is pointed by BX register, right? So this is the example of register in direct addressing mode. So offset address is in BX and it is in data segment because the default segment for BX register is data segment. So the content from the memory whose offset address is in BX in data segment will be added with AL. We can use base index addressing mode also, BX SI. So now content of AL will be added with data whose offset address is BX plus SI, right? So I have offset address of our data which is in memory is calculated by adding the value of BX with SI, and this is in data segment. So in this way we can access our data in the memory by direct addressing mode, or by register indirect addressing mode, or by based index addressing mode, or relative register indirect addressing mode. So there are various ways. So you can access your data in any way. Now another case is at AX comma within bracket 1000. Now here, since our destination is 16-bit, this indicates that there is an addition of 16-bit number, right? So one 16-bit number is in AX and second 16-bit number is in memory, right? Now in memory, whatever offset address is given with the instruction, at this offset address, the lower 8-bit of our 16-bit are stored. Right? For example, let us assume in AX we have some value 3294H. Right? This is the value of AX. Now at 2000H colon 1000H we are having some 8-bit number 23. At next offset 2000H colon 1001H we are having another 8-bit number, that is 19H. Okay. So at 2000 colon 1000H, this 1000H, here we are having number 23H. At the next offset 1001H we are having another 8-bit number 19H, right? So when we access this number in this instruction, add AX comma 1000H. So in this instruction, since the destination register is a 16-bit register, that's why the 16-bit value from the memory will be accessed for the addition. And whatever offset address is given with the instruction, that will be at that address, lower 8-bit of the data is there. So at 1000 offset we are having 23. So 23H, and at the higher offset, that is 1001, we are having 19. So this is 19. So this is our data. This is our data 191923H. This is a 16-bit number. This will be added with the value of AX, right? This will be added with the value of AX. And finally, the result will be stored in AX register. So in this way, we can perform the addition over 16-bit number. Now third case is just similar to the second, only thing is our destination is memory. For example, add 1000H comma AL. So here see the register. Register is a 8-bit. So this will indicate there is a addition of 8-bit number, right? So value of AL will be added with the memory whose offset address is 1000H in data segment, right? So So this addition will take place, and finally result will be stored in destination, that is ds colon 1000h. Here result will be stored. So these are three forms of add instruction. Now in the simplest form, suppose we want to add two numbers, two 8-bit numbers, right? Numbers are 23h and 11h. Simply we want to perform these two additions. So simplest method is, what we will do, move AL, 23h. We will write this instruction. With this instruction, this 23h will be stored in AL register. After this, we can directly write add instruction. Add in this we can use data also, immediate data also. We can use immediate data, right? Just as I am writing the instruction, add AL, 11h. So this is the case of immediate data. So with the instruction, one of our operand is in AL register, and second operand we have given with the instruction, right? So the addition, the operation will take place, and in this operation the value of AL will be added with the immediate data 11h, and result will be stored in AL. So here 3 plus 1 is 4, 2 plus 1 is 3, 3, 4. So after the execution of this instruction in AL we will find 3, 4h is stored in AL register. Now we will see if we are going to add more than two numbers. If we are going to add more than two numbers, suppose we want to add three numbers, right? 21h, 31h and 41h. We want to add these three numbers. So one method, simple approach is move AL, 21h. First number we will bring in AL. After this, add AL with second number. So with this instruction, with first instruction, AL will become 21h. With the second instruction, AL will be equal to AL plus 31h, right? So in AL already we have loaded 21, so here it is 21h. So 21h plus 31h is, this is 52h. So after this instruction, the result of the addition of first two numbers is in AL, right? In AL we have 52h. Now again we will repeat the add instruction, add AL, third number 41h. So now in AL we have 52h and immediate data is 41h. We add these two numbers, so result is 4, 9, 94. 94 will be stored in finally AL. So this is our result. And suppose if you want to add 4 8-bit numbers, then again we include another add instruction. If you want to add 10 8-bit numbers, then 10 times we have to write this add instruction. So in this way, if we are increasing the numbers, then add instruction is increasing. So we have to find a solution in which the program should be independent of the numbers, right? If we are adding 3 8-bit numbers, the number of instructions should be same as when we are adding 10 8-bit numbers. So we want to develop one standard program which can perform the addition over any number of 8-bit numbers, right? So first we will start with, we will develop a program for the understanding to add 3 8-bit numbers, right? So let us assume our 3 numbers are stored in the memory location 2000H colon 1000H. Here we have first number. Second number is at 2000H colon 1001H. Here we have second number, and 2000H colon 1002H. Here we are having third number. So all of these are 8-bit numbers, right? So these are 8-bit numbers. Here this is our data segment and this is the offset. So we want to perform the addition over these 3 numbers, and whatever is the result, we will consider result of 8-bit, right? So result we will store in 2000H colon 1020H, right? In memory at the offset 1020H, at this offset in the same segment we will store the 8-bit result. So now to perform this operation, first we will do the initialization of data segment. For this, move AX comma 2000H. Then I will move the value of AX in data segment register. So by this, data segment register will be initialized with 2000H. Now I will store the offset address of my first number, that is 1000H, in one register, right? In SI register I will use move SI comma 1000H, right? So this is, I will write the comment here, offset address of first number. Now the offset address where I want to store my result, that I will store in some another register. Move, I will use DI comma 1020H, right? So this is offset address of result. Now I will use the counter which will inform the processor that all the 3 numbers addition has been completed. So the logic which I am going to use, in that logic, if we are adding total 3 numbers, then the value of counter we will take 1 less than that, right? So if we are adding 3 numbers, then value of counter will be 2. If we will add 10 8-bit numbers, then I will use counter 9. So for counter I will use register CX because in future I am going to use instruction loop. So here move CX comma 0002H. So this is counter. Now I will bring first number in AL register. So move AL comma within bracket SI. So in SI, right now we have 1000H. So data from offset address 1000H of data segment 2000 will be moved in AL. So first number is in AL. Now I will bring the address of my second number, the offset address of my second number in SI, right? For this simply I will use instruction INC SI. With INC SI, the value of SI will increase by 1. So in SI we are having 1000H. So now it will become 1001H, which is the offset address of my second number. And now I will add 2 numbers. Add AL. In AL we have first number and within bracket SI. In SI we are having the offset of second number. So the first number and the second number will be added and the result will be stored in AL. Right? So after the addition of first two numbers we are having a result in AL. Now I will check whether we have completed all the additions or not. So for that, if we decrease the value of CX, DEC, and after that if I check zero flag, jump no zero, then repeat. And for repeat, I will come here. Means what will happen here? DEC CX will make CX register decreased by 1. So now CX will become 0001. Now since CX is not 0, right? That's why jump no 0. This instruction will send the program to the label repeat. Again the program come here. Then INC SI. It will increase the value of SI by 1. Now SI will become 1002, which is the offset address of my third number, right? And then add AL comma within bracket SI. In AL we are having the result of addition of first two number. That will be added with the third number whose offset is in SI now, right? So now addition will take place and final result is in AL. Now DEC CX. Now CX will again decreased by 1. So previously CX was having 0001. Now it will become 0000. So now the value of CX is 0. So jump no 0. This instruction will not send the program to the repeat because CX has become 0. So now the instruction written after this will be executed, right? So controller will come to this place. So here when controller will come to this place, this indicates that addition of all the numbers is completed and our final result is in AL, right? So now simply store that result in where you want to store. You have to store at 1020. That address we already stored in DI. So here I write simple instruction move within bracket DI comma AL. And after this halt. So in this way 3 numbers addition will be completed, right? So we will take these numbers. Suppose our first number is 23H, second is 49H, third is 22H, right? So one by one we will go and we will check. So move AX comma 2000. In AX we are having 2000. Move DS comma AX. So in DS we are having 2000H. Then third instruction move SI comma 1000. In SI we are having 1000H. Then move DI comma 1020H. So in DI we are having now 1020H. Move CX comma 0002H. So in CX we are having 0002H. Then move AL comma within bracket SI. So in SI we are having 1000. So data from physical address DS colon 1000H, right? In DS we are having 2000H. So data from 2000H colon 1000H physical address will be calculated and from there a data will be moved in AL, right? So in AL what we have now? In AL we have number which is at offset address 1000H. At 1000H we are having an optional value 23. So in AL we are having 23H. Now INC SI. So SI will be increased by 1. Now it will become 1001. Add AL comma within bracket SI. So it will add the value of AL and the value of the memory whose offset address is in SI. So in SI we have 1001. So at 1001 offset we are having number 49. So this will be added with the value of AL. So 23H, which is the value of AL, will be added with 49H. The result 9 plus 3 is C, ABC. 6C. Now this is the result which will be finally stored in AL. So in AL we have 6CH after add instruction. Then DEC-CX. So CX will become, now from 2 it will become 1. Jump no 0. Now it is not 0. So go to repeat. Program will come here. Here INC SI. Now SI will again increase by 1. SI 1001. It will become now 1002. Then add AL comma within bracket SI. So the value of AL will be added with the data whose offset address is in SI. In SI we have 1002. At 1002 offset we are having third number, that is 22. So 6C will be added with 22H. So C plus 2 E. 6 plus 2 8. 8EH. This is the result and which will be stored in AL. Then DEC-CX. CX is again decreased by 1. So CX 0001. Earlier it was this, now it will become 0. Now CX has become 0. So jump no is 0. Will not send the program to the label repeat. This instruction will not send to the label repeat. The next instruction after this will be executed. The next instruction is move within bracket DI comma AL. So value of AL will be stored in the memory whose offset is in DI. So in DI we have 1020. At this offset the value of AL, which is 8E, will be stored. So here at this the result 8E will be stored and finally halt. Program will stop. So in this way this program will perform the addition. Now you just think a situation where we are having three numbers like this, F3H, 21H and 72H, right? If we add these three numbers, then you see what will happen. First two numbers, add F3 with 21H. 3 plus 1 is 4, F plus 2 is 1, 1. This is 1 and 1 carry will be generated, right? This is 1 carry. And this is the 8-bit number. And here it is carry, right? This is the result. Now with this, add 72. 4 plus 2, 6, 7 plus 1, 8. And already there is 1. So the result will be 186 in hexadecimal. This is the result. This is the result, right? But if these three numbers are added by this program, then you will get a result 86. There is no provision in this program which consider the case when carry is generated, right? So if we check the result, result will be this 86. Though here in this case the result is 16-bit, right? Result is 16-bit because this 1, this is 186H. If you write this number in binary in the 16-bit format, then this 6 is 180,110. 8 is 1000, 1. This 1 is 0001, and to make it 8-bit, you keep it here 0, 0000. This is the 8-bit. This is the higher 8-bit, and this is the lower 8-bit. Result is 16-bit. So in this particular program, we are not having any provision to consider the carry, right? So now we will change our program in such a way so that if carry is generated under any condition, then we store that carry also, right? So now we have to perform the addition on 3 8-bit numbers, and the result is 16-bit. The result is 16-bit. Now if the result is 16-bit, then we have to store our result in 2 memory locations. So our result will be stored at 2 locations, 2000H:1020H and at 2000H:1021H. At lower offset address we will store 8 LSBs, and at higher offset address we will store 8 MSBs. So our result is here. So how to write the program for this particular operation where we are adding 3 8-bit numbers and result is 16-bit? So that we will see in next lecture.